Now that we are done with the standard undergraduate control material, we move on to the second part of this course, which talks to more advanced ideas in control, such as control of inverse response systems, control of unstable systems, time delay systems, and so on. And we will also talk about other control structure designs such as feed forward control, cascade control, which basically implement some form of multivariable controller within the single input single output controller framework. Then we will look at truly multivariate control. We will first look at how you could do pairing for multivariable control systems to break them down into CISO control systems. And once we learn how to do the pairing, then basically the CISO control systems ideas are whatever we have seen till now. So, there is no change that happens there. And then we will finally look at implementing these controllers in a truly multiple input, multiple output framework. So, that will end the second part of this course. So, the ideas of inverse response, unstable control, and time delay systems are easily understood when we think about controller tuning using a direct synthesis approach, because that will allow you to understand what are the issues that come about if you have these types of process behavior, and what are the fixes which will become readily apparent when you look at this direct synthesis kind of tuning. The cascade and feed forward control and so on are what are called traditional advanced control, slightly more advanced than simple CISO control. However, you do not need anything really extra other than the standard CISO ideas to understand them. And in fact, industrially, when these types of controllers are implemented, they are implemented as blocks in your standard DCS system that one has. So, that is the reason why these are called traditional advanced control. While the ideas are slightly advanced, they can be implemented in traditional single input single output control systems. And then we will have the truly multivariable controller, which could be looking at all the variables all at the same time, and then how do you think about either decoupling them or treating them as truly multivariable systems. Okay, so, that is going to be the overview of the second part of this course on analysis, design, and assessment. So, this is lecture 19 of this series of lectures. So, since we are talking about dynamics which are more difficult to control, we will start with the first dynamic behavior, which is more difficult to control than standard systems, and this is called an inverse response behavior. What I am going to do in this case is actually I am going to describe inverse response behavior purely from how the transfer function looks. Okay. So, till now I have been really emphasizing that these transfer functions are embodiments or representations of a physical system. So, I have been saying ultimately we keep looking at transfer functions, but do not forget that these come out of physical systems, and the parameters in the transfer function are actually computed based on physical dimensions of the system or operating conditions and so on. In this case, I am actually going to start with the transfer function and explain what inverse response means. So, the reason why I want to do it like this is when you look at a transfer function itself, you should be able to understand the complicated dynamics that might ensue from this form of a transfer function. And once we do that, I will kind of explain to you intuitively why this inverse response behavior is difficult to control, and that I will go back to my standard bike example, which seems to provide us enough richness to explain many of these ideas. And then I will also talk about physical system where you will see inverse response. And I will tell you something, this inverse response is not very uncommon. There are several systems which show inverse response behavior, and if you look at literature, you can look at different systems which will do this. Okay, so let us take a transfer function. Till now, whenever we have talked about transfer functions, we have talked about a numerator by denominator, and we have talked about the roots of the denominator. We talk about how we can do partial fraction in terms of the roots. We have talked about writing the denominator in a root resolve form. We have talked about identifying the roots of the denominator polynomial without ever computing them. in terms of where they are located and so on. So, our focus has largely been on the denominator if you look at all of the traditional control that we have talked about. And I also mentioned it is not that the numerator does not play a part in our partial fraction expansion. Each of the coefficients for each of these terms actually somehow captures collectively the numerator polynomial. Nonetheless, our basic assumption was this numerator polynomial was not creating any special difficulties for us, so that we could really focus on the denominator polynomial and look at this. And purely from an analysis viewpoint, if I wanted to do an inverse Laplace, I really needed to know only the denominator polynomial root resolve form, and then each term can be individually inverted, right. So, there again numerator polynomial plays a role, but not explicitly, it is just the coefficients are computed based on the numerator polynomial. And when we come to stability again, if you are really looking at the denominator polynomial, then again you are not really paying much attention to the numerator polynomial. And when it comes to tuning, and when you talk about stability based tuning, again you are looking at the limits of stability. So, how far I can push the system with control parameters, and then you are backing off based on that. Again the controller design also did not seem to bother too much about the numerator polynomial, because the ultimate period and ultimate gain, all of these were computed using the denominator polynomial. Okay. Then when we go to performance based tuning, which is what we call as the direct synthesis approach, where I am given a certain performance metric in terms of a closed loop transfer function, and then you ask what is a controller that will get me this closed loop transfer function. That is a real first time that this numerator is going to start playing a bigger role, and understanding the numerator polynomial is going to start playing a bigger role, because if you notice the expression for the controller, you have a 1 over g model. Okay. So, since you have the model transfer function coming in the denominator of a controller calculation, which is what we do when we do direct synthesis. Now, interestingly, what happens is, if I have a transfer function like this is the numerator, this is the denominator. Somewhere in the controller calculation, I start having this g model s in the denominator. So, that basically conceptually what happens is, then this flips it to ds by ns. Okay. So, the numerator polynomial somehow seems to come to the denominator, and if you want to now think about the stability of the controller, for example, right, then you have to start paying attention to the numerator polynomial, because it has come in the denominator. So, when you explicitly do this direct synthesis, and because in the direct synthesis formula you have a 1 over gm, the numerator in the model becomes now the denominator, and then you got to start worrying about what is happening in the numerator. So, that is an interesting thing that happens, and this comes out very beautifully from that simple calculation where we did the direct synthesis controller. Now, we will try and explain what happens when there are issues with the numerator polynomial. And clearly the issues will happen if the roots of the numerator polynomial, which we call as the zeros of the transfer function, have certain behavior. So, just to recap, if I have ns over ds, the roots of this polynomial we call as the poles of the transfer function, and the roots of this polynomial we are going to call as the zeros of the transfer function. So, now let us look at a particular transfer function form, and then try and see whether we can understand what happens, and then we will come back to what inverse response behavior is, which is basically in words defined by this. We will say systems where the initial direction of change is opposite to the final change. Okay. So, initially it goes in one direction, but ultimately it settles down in the other direction. So, the way to think about it is, because in control we have always been talking about deviation variables. So, at the initial value it is always, we think about the initial value as being 0, and if I have to interpret this and then say finally the variable becomes positive, then if it is an inverse response system, the initial direction of change will be negative. So, it will become negative for a short period, and then maybe it will become a positive value. Or in the flip side, if the final value is negative, it might start being positive and then finally settle down to negative value. So, the initial direction of change, how long the change happens is a different question, but if the final value is either positive or negative, at least for a short period of time, the initial value would have been negative or positive respectively. So, that is the key idea of inverse response. Now, you might ask, this sounds like a very strange thing to worry about. Why would someone worry about this is one question, and the direct synthesis approach is going to give you a nice answer as to why you should worry about this. Okay, so, that is something that will follow. But before we actually worry about this, we also have to think about how. So, if this is something that I need to worry about, how do I just look at the transfer function and then see whether the system is going to have this inverse response behavior. So, it is another question that we need to answer. Okay. So, the first answer, if you just look at the transfer function, if you want to understand whether this process which is represented by this transfer function has an inverse response. So, what you do is, for the first time I am going to tell you, focus on the numerator. Okay. So, when you focus on this numerator polynomial, if you look at this numerator polynomial, you will see that this has 1 0, because there is only one root, because the numerator polynomial is of order 1, and the denominator polynomial is of order 2. So, I have 2 poles. So, I have 1 0 and 2 poles in this transfer function. Now, let us just quickly think about the poles, because we have done this many times. So, let us quickly kind of dispense with these poles in this example. So, if tau 1 and tau 2 are positive, then the poles are in minus 1 over tau 1 and minus 1 over tau 2, and these poles are in the LHP if tau 1 and tau 2 are positive. That means the system is stable. Now that we have talked about the poles, let us go to the 0 of this transfer function, and if you look at this transfer function, it has 1 0 where the numerator goes to 0, which is at 1 over z. This is 1 minus z as 0. So, z is 1 over s is 1 over z. Now, if z is a positive number, then you notice that this 0 is in the RHP. Okay, remember. So, this is how we look at this. So, in this case you might have a minus 1 over tau 1 here, minus 1 over tau 2 here, but this is 1 over z, right. If a pole had been in the right half plane, we would have said anyway the system is unstable, but actually the system is not unstable because all the poles are in LHP. However, we have a 0 in the RHP. Okay. So, inverse response systems are typified by zeros in the RHP. So, the first question that I asked we can answer, which is to say that if I look at the numerator polynomial and I find that there are zeros in the right half plane, then I have to worry about inverse response system, and if I have only one 0 in a right half plane, that system will show an inverse response behavior. And the generalization of this result is, if I have an odd number of zeros in right half plane, the system will show a inverse response behavior. That is a generalization of this, but as far as this course is concerned, we are going to largely look at a maximum of 1 0 on the right half plane. Most of the time there might be an odd case where we will have more, but and when you have 1 0 on the right half plane, then you have to assume, or you are guaranteed that this system is going to show an inverse response. Okay, let us first understand how we say that this is going to show an inverse response. Mathematically, how are we going to understand this inverse response behavior is something that we can see. So, here we said, look at it carefully, we said the initial direction of change is opposite to the final change. So, this is talking about the rate, whereas this is talking about the final value. Okay. So, the minute we say final value, then we know that from our bag of tricks we have something called a final value theorem. So, we will take this system and then try and see what is the final value for a step change. Okay. So, if I have a step change from before, we know this y of s will be g of s times 1 over s. So, y of s is here, I have g of s over 1 over s. So, this is y of s. So, if I want the final value for y, which is limit t tending to infinity y, okay, y of t here, then I know that from a final value theorem this is limit s tending to 0 s y of s. Y of s is this transfer function times 1 over s. I am multiplying this 1 over s because we are subjecting this system to a step input, and s y of s. So, I multiply this s this side, and then I can cancel this s and s here, and then when I set s equal to 0, okay, what I am going to get is this is going to go to 0, this is going to go to 0, this is going to go to 0. So, I am basically going to get the final value as k. So, if k is positive, the final value is basically a positive number. Okay. So, this I think is something that we have seen several times before. So, it should be straightforward to understand. Now, if this system is going to show inverse response, then the initial direction of change has to be negative. So, let us understand what direction of change means. So, if I am looking at y, so y of t, okay, limit t tends to infinity y of t is the final value, the final change from 0, right, because always our base is 0 because we are looking at deviation variables. So, the initial direction would mean I want to know what this dy by dt. So, what direction is it going to start moving. So, if this is negative, then I start at time t equal to 0 at value of y equal to 0, and if dy by dt is negative initially, at least right after this system start responding to the step input, it has to go in the negative direction because dy by dt is negative and I start with 0. So, I have to get negative numbers for y, and this only talks about what happens initially. We have already shown finally y is going to take a positive value from the final value theorem. So, how do I find out what limit t tending to 0 dy by dt is? And whenever we have t tending to infinity, we have to use the final value theorem, and whenever we have t tending to 0, then we have to use the initial value theorem. And the final value theorem you have to set s to 0, and the initial value theorem you have to set s to infinity. This is something that we have learned from our previous Laplace transform lectures. There is also another difference here. Here we are looking at y of t, but here we are looking at dy by dt, but that is not a big deal because we know the Laplace transform of dy by dt is s y of s. So, this is something that we already know. So, what is going to happen is when I want to get this limit t tending to 0 dy by dt, that is going to be limit s tending to infinity Laplace of dy by dt, and Laplace of dy by dt is s y of s, and this y of s is g of s times 1 over s because this is a step input. So, this term here Laplace of dy by dt. So, this is going to be this here because this s y of s, this s comes for the dy by dt and 1 over s comes for the step response. So, that and that will get cancelled. So, I will be left with 1 s which is outside here. So, when you do this math here, then what you will do is, so you take this, then you take the s out of this, then what you will have is s squared times k times 1 over s minus z divided by, so if I take both s's outside, I will have s squared, okay. I will have, since I have taken the s square out, I will have tau 1 plus s, tau 2 1 plus s, okay. So, this is what I will have. Now, this s squared and s squared I can cancel, and then when I substitute s equal to infinity, you will see that I will get a negative rate of change. Okay. So, what it basically says is that the final change, while it is positive, the initial rate of change is negative. Okay. So, let us take an example to understand this. Supposing I take this example here, g is 1 minus s divided by s squared plus 2s plus 1, and this is a MATLAB simulation of response to a step input, and clearly you can quite easily see that this s squared plus 2s plus 1 is actually s plus 1 whole squared. So, basically this is minus 1 are the two poles. So, the system is stable because the poles are on the left half plane, but the 0 is s equal to 1. So, this 0 is on the right half plane. So, this satisfies this 1 right half plane 0. So, basically you would expect the response to be of in the inverse response type, and you can actually see from the simulation here that the initial rate of change is negative. So, I am starting at 0 here, and because the initial rate of change is negative, so the curve has to go in this direction because dy by dt is negative here, but the final change is positive. So, it goes back to a positive value. So, it goes down and then goes to the final value. So, you might actually think and say, okay, why do we worry about this so much? Why should this create any control related issues? So, before I answer that question, and again like I said before, I will look at this bike example to explain why this creates a problem. But before that, I have to at least give you one example of a physical system which will do this inverse response. A typical system that people talk about is level control in boiler drums, where you see this inverse response behavior. And the idea here is the following: supposing you have a boiler and you are heating it so that you have steam coming out, and supposing you say I want to increase the level of the liquid in the boiler. Now, in all our tank example and other examples, we have seen that if you want to increase the level of a liquid in a tank, what you do is either you cut down what goes out of the tank from steady state, that will increase the level of the tank, or from steady state you can increase the amount of input into the tank so that the level increases. So, if you do the same thing and then say, okay, I want to increase the level, so let me feed some liquid into it. Typically in a boiling liquid you will have these bubbles in the liquid and it is producing steam, but when you add new liquid which is at a much lower temperature, then it might cool down the top of the liquid, in which case these bubbles might collapse, and because of that the volume occupied comes down. So, the level comes down a little at the beginning, but ultimately once you have really increased the amount of liquid, and if the steam rate that you are taking out is remaining the same, then ultimately the level has to go up. So, typically you would see level decreasing as soon as you increase the amount of liquid into the tank, and then after a while the level will of course go up. So, you see that you will have an inverse response. So, this is a very typical example that people talk about in terms of the level of the liquid showing inverse response in a boiler drum. So, that is an engineering system, and there are lots of biological systems which show inverse response. There are several other systems where you can see this inverse response behavior. Now, the last question that one might ask is, why is this important, right? What is the difficulty that this introduces in control? And this is where the direct synthesis approach really tells us what is the difficulty of this, because if you recall from the direct synthesis formula, you have 1 over Gm, and if the model has 0 in the right half plane in the numerator, when you invert this for a controller calculation, then basically what happens is the right half plane 0 becomes right half plane pole for the controller, which will make the controller unstable, which is something that you do not want to happen. So, basically what it says is, if you have, let us say, a desired response that you want, till now whatever was the desired response, I could design a controller based on the desired response by using the formula for the direct synthesis controller. But now for the first time, if I have a model which has a right half plane 0, then when I want to design a controller and I know what I want, so I give you a G desired, and if I am not willing to make any compromise and then say this is a G desired and you have to design a controller for this, if you go ahead and design the controller based on this G desired, then your controller will become unstable. So, which is something that you do not want. You do not want for many reasons. Number one, it is not realizable. You have to understand, when in mathematical terms, when you say a controller will become unstable, that basically means that supposing it is a water line and you are asking for water flow to be increased, when a controller becomes unstable, it is going to ask for more and more water to be flown through that line, but there is a physical limitation, right. So, the water you cannot flow more than that amount of water, because if you try to flow more than that amount of water, you will burst the pipe, right. So, that is how the physical connection to the unstable thing comes. Mathematically it is okay, U keeps increasing, so what is a big deal, but physically you cannot increase beyond a certain number because physical limitations are there. So, it basically says that now for the first time we are faced with a process which limits the performance that I can get from a controller, and it limits in the sense that I do not have an unconstrained ability to say this is what I desire and please give me that, right. So, if I ask for something that is desired, if the controller has to give me what I desire, it has to become unstable. Okay. So, there is a physical limitations on how much I can desire in some sense. So, that is the performance limitation that comes. So, the philosophical answer to this problem is to say, okay, I have to moderate my desires because the process is not going to help me get whatever I want. So, I am going to moderate my desire to be in line with what the process allows me to get, and that is the concept of designing a controller when you have these performance limiting factors in the process model itself. And this is an interesting idea which comes out beautifully from just the direct synthesis equation. Now, I have explained this to you mathematically in terms of what is this inverse response behavior. So, basically you have to look for zeros in the right half plane, and if I have odd number of zeros, then the system will exhibit inverse response behavior. I have conceptually told you why this inverse response behavior is a problem. In fact, before that I actually showed you what the behavior is in terms of a simulation. So, the initial direction of change is different from the final value the output takes, and I have also conceptually told you how this limits the performance that a controller can provide because of the 1 over GM term. Now, the last thing, and I also told you that there are engineering examples. I gave you one very commonly used example for this inverse response. Now, if I want to understand this little more physically, why inverse response systems are difficult. So, think about driving a bike on a road, and at some point you decide that you desire to turn right. Okay. So, the desire from a control system's viewpoint is that I want to turn right, and then basically you are going to, so the manipulated variable in this case is the steering wheel. So, you say if I move my steering slightly to the right, then I will go right. So, that is our intuition, right. So, a normal bike, when you are driving and you want to turn right, you will turn the steering a little bit and it will go right. Supposing for some crazy reason the manufacturer has given you an inverse response behavior bike, then what will happen is the following. So, when you are going and you want to turn right, then of course you have to move your steering to your right, because the ultimate change in direction is going to be right. However, because of this inverse response, let us say I move my steering a little bit to the right. So, the initial direction of change is opposite to the final, the opposite to the final is it will move left. So, you are driving a bike and you are trying to turn right, and then suddenly this turns left. So, you move your steering to your right, but the bike is moving to the left. So, what is going to happen is that you are going to get completely confused. You are saying, okay, I wanted to turn right, but how is this going left? So, you are going to try to compensate. Then you will say maybe I should turn left and then it will turn right, and you will turn left, and that will completely create havoc, because you will keep trying to turn right and left because you are not understanding what the bike is doing. So, this is the same thing that happens with control systems if they are not designed properly, because what we expect to happen will ultimately happen, but because something else happened, our brain will say, okay, there is something wrong and I have to do something about it, and the same problem will happen in terms of inverse response behavior and when we control for inverse response behavior. Of course, the solution to this is obvious, how you should solve this bike problem if you are a smart individual. In the next lecture, I will talk about how you solve this problem as a smart individual, and then we will go on to what it translates to in terms of the math as far as controlling inverse response behavior is concerned. Okay. So, in the next lecture I will talk about how you control these inverse response systems, which basically create performance limiting behavior. Thank you.